So we're about to begin our two-dimensional unit, and I like to start with forces rather than motion because I feel like we can consciously pull in multiple dimensions and we can make it feel a little more real. We have to remember that as we're doing this unit that we're not learning any new physics. All the rules we learned for one dimension are true. We just have to keep track of them in multiple dimensions. So I want to go back to the force picture, or the free body diagram, sometimes it's called. Somebody's standing still on the ground, and that's what I have over here on the left. And hopefully what you're seeing there is pretty familiar to you. We have an upward normal force on this person, a downward force of gravity. So we can write sigma F equals ma, and we can replace our sigma F with the two forces. And as you can see, the acceleration for someone standing still is 0. So the two forces are canceling each other. So for this person, since they're not accelerating, we know the forces have to add to 0. And that's going to be the big idea for our first lab in 2 dimensions. We're going to have to make the forces go to 0. So let's go over and look at what 2-dimensional forces might look like. Now there's a lot of scary looking things here, and we'll go into it all, and we'll make sure it stays familiar to you guys. But if you look at this force picture here in the middle, you can see that there's a rightward force, and there's two forces that go both left and up, or left and down. What I did with those two forces is I made them into triangles. So for example, if we look at F1, it goes left and up. I have this thing called F1x, which is the left part, and F1y, which is the up part. So since the iron rule of 2 dimensions is the Vegas rule, what happens in x stays in x, what happens in y stays in y, we're making these triangles in order to figure out which part of these diagonal forces are horizontal and which part are vertical. The only thing you really need to know for this new unit is that just like before, force is at 0 if there was no acceleration. That's still going to be true. But if you look over on the right side of the screen in red, it says sigma fx equals ma. Every force that says left or right adds to 0. And if you look over to the right side of the screen, where it says sigma fy equals ma, every force there is adding to 0. So in other words, it's the same physics as before, but we've just got multiple dimensions. So I want to introduce the device that's going to teach us how we can study these forces, and we'll play with it for a little while, and then we're going to go through and figure out how we do all this math so that it doesn't look so scary. I've got here an interesting device called a force table, sometimes a force board. It's a great way of seeing how forces add and subtract in multiple dimensions. So how does it work? It's a big metal disc, it's got notches in it, and on those notches you can put these fish scales. Let's zoom in and take a look at one. If I pull it, you can see there's a spring inside, and the more I stretch the spring, the more that little arrow goes down the scale. It's measuring the force on the spring. Physics class, we usually call these spring scales. Most normal people call them fish scales, because if you go fishing and hang a fish from this part, and then lift this part up, you can see how much the fish weighs. They're a great way of measuring force. And they've got kind of an interesting setup here. They're all linked together in this ring. So the ring's not accelerating. It's standing still. Its motion is constant. And what that means is that in all dimensions, there must be no net force. The force has to add to 0. Sigma f is 0. So what dimensions are there? Well, it's a plane, so that means 2. And we can specify the x and y axis however we want. So I made a little reference frame here. And I'm going to make this my x and y axis. In other words, the two scales currently hooked up are along the y axis, and I'm going to pull this guy, and you in lab are going to pull this guy towards the right. And our reference frame is not moving, just this piece of paper is. This is always going to be the y-axis. This is always going to be the x. So let's look at what the scales are currently doing. As you can see, they're reading about the same. They've already got some force on them, and that force is equal, showing that all the upward force from this one is being canceled out by downward force from that one. That has to continue to happen. The forces in the y dimension have to sum to 0 if the ring is not moving. But look what happens if I pull the third one to the right. Obviously all three scales increase. But now the two that were just pulling up are now pulling back to the left. But they're still pulling up or down. And that's kind of the key thing. This rightward force, because the ring is not moving, has to be canceled out by a leftward force. Where's the leftward force coming from? The two scales that were previously just up and down. Now they're still up and down, so they also have to be providing forces in that dimension. So the two original scales are doing two things. They're both providing leftward forces and upward forces, and downward forces, I guess. So how do you keep track of all this? How do you see what part of the two original forces goes to combating the new force? You have to do a sum of force equation in each dimension, and that's what you're going to be doing in lab. So I have an example of the force board, and I've got the math worked out for this particular set of three scales over to the right here. The horizontal left-right forces are in red, the vertical up-down forces are in green. And you'd be forgiven if you think that this looks like a complete mess. But in putting all this on paper, I'm following a process. I'm starting at a certain point and following steps, just like I did for one dimension. And if you learn that process, you'll become familiar with it. So I'm going to walk you through how I built this calculation, and then you're going to do it for several of your force board forces. The process starts pretty simply. You draw your forces and you write sigma F equals ma for both horizontal, which has an x after the F to show horizontal, and vertical, which has a y, x and y axis. In general, you're always going to draw the forces and write sigma F equals ma for both dimensions. In this case, the reason it's 0 is because the ring in the middle was not accelerating. So all forces in both dimensions have to cancel. Typically, one of the forces will be unknown. Here, everything's known, and all we're doing is checking to see that these forces really add to 0. So first step is draw your picture. Write sigma F equals ma. The next step is going to be to start listing the forces that act in each dimension. So let's zoom in and see what that looks like. I like to use the words up, down, left, right to describe each force. Notice I've drawn my axes. We're going to call up, down, y, left, right, x. So the three forces, F1 is left and up, F2 is left and down, and F3 is right. So I've coded in red left and right. If we go over here to sigma F, you can see what I put here. The rightward F3 minus the leftward F1 and the leftward F2. Notice F2 and F1 have an X after. That's to signify that it's not all of F2 and F1 that we're talking about, just the part that goes left. Right positive, left negative. If we go over to our Y forces, we see F3 is missing because F3 doesn't have an up or a down. So we have the up minus the down. And notice these are y's because it's only the y part that we care about here. So that's step 2. Step 3 is to start trying to get these F1x, F2x, all that stuff. We do that by taking each force that's at an angle and turning it into the hypotenuse of a triangle. The sides of that triangle will correspond to what we're looking for. Here, F1x is the left part of F1. F1y is the up part of F1. So now these labels that we had in our two sum of force equations, they're actually now on our picture. And we're just going to use trig to try to solve for what these sides of the triangles are. So if we look at how we solve for this, we see that we write sine and cosine for each angle that we're interested in. I've called the angle here theta for F1, and I've given it a different Greek letter, phi, for F2. And so these over here have to correspond to the top force, these correspond to the bottom force. Let's zoom in and take a look. So by writing sine and cosine, you actually get two equations, one which has the unknown F1y in it, and one which has the unknown F1x in it. Since sine theta and cosine theta are just numbers, these are really solvable equations. We can get F1y and F1x directly. And similarly with F2y and F2x. All we need is sine theta and cosine theta. Notice that we do have the angle from F3 to our force, which is 110 degrees. Theta, of course, is going to be 70 degrees because those two have to add to 180. So what we're going to do here is we're going to leave that 110 in there, and we'll end up getting some numbers. That would have been very similar to if we had put in the 70. And the only difference with putting a number greater than 90 in there is occasionally we spit out a negative number. And that negative number actually is appropriate. Notice that this is a minus 0.342, and that's corresponding to the fact that this is in the minus direction. But most of the time it would be easier just to call it 70 and to remember to put the negative there because it was pointing in the minus direction. If that went over your head, don't worry about it. I actually have a set of pictures here to talk about similar triangles and why angles like that give similar sines and cosines. If you're interested, you can take a look at it. But the key thing is our sines and cosines give us simple equations where we can solve for F1y and F1x, and similarly F2y and F2x. And that means we should be able to plug it in to these equations. So here's our final answers, and F3 just got plugged in full, and then the orange side of this triangle gets plugged in here. The teal side of the bottom one gets plugged in here, and we can see that we get about 0. The 0.46 is significantly less than any of the actual forces we were looking at in the lab. And a similar thing happens over with vertical. The brown side is 7.4. The pink side of this one is 7.99. So we get about 0 again. And that was the whole point of this lab, just to go through the process of summing up forces in 2 dimensions and to verify that what we know needs to be true, no acceleration, therefore a net force of 0 is true. So I'd like you to go through in your labs and practice several of these. The more you do, the more comfortable you're going to be. And if you look at this picture and are intimidated by it, keep in mind it's just following those steps. Sigma F equals ma in both dimensions. Label your forces with up, down, left, right. make decisions about which forces belong in each, and then do a little bit of trig, just sine and cosine, to break each force down. You'll get where you need to go. You should have a variety of different problems to do, because in the lab, again, you pulled that right spring scale more and more to the right each time. And as your rightward force increased, that meant that the two forces that could pull leftward also had to increase. So you don't have to do all the different ones I just did here, but I think 3 or 4 of them would be good to making you feel like you've got enough practice here.